Good morning. In this video, we'll continue the discussion on soil exploration. Now, in the previous few videos, we have been discussing the soil exploration briefly, and we discussed what the guidelines are for soil exploration, what are the objectives of soil exploration, why it's important to carry out the soil exploration, etc. We'll extend that discussion to the different methods of soil exploration. It starts with auger boring, then you have wash boring, then you have the rotary drilling, then you have the percussion drilling, the core boring, geophysical methods, and of course open pits and trenches, which strictly in the sense they're not quite scientific, but anyways you do have an option to carry out an open pit or a trench. You dig out the hole and try to see if the soil there is of your preference, etc. I've added a gap here because the last one, the open pits and trenches, are not quite strictly in the sense of scientific aspect of soil exploration. But anyways, we'll limit our discussion to auger boring and wash boring because that's what is included in your syllabus. Now, auger boring, auger, the material, the equipment is quite similar to the one that is used by a carpenter or maybe a bottle opener. You might have seen a bottle opener or a carpenter using these kind of augers, right? So I've added a figure from the internet which mentions something about the helical auger, looks like a spiral here, and a post hole auger, which is used to grab the soil once the hole is made. And you do have extension rods like this, which can be used to go deeper into the soil profile. Now, anyways, what you need to understand is that augers are nothing but spiral kind of equipments which can be turned into the soil, and it has a stem with a cross handle, right? It has a stem here and a cross handle. So people, men, the labor at work, will kind of twist and apply torque here on the cross handle, and it screws it down into the soil. So it can be actually operated manually or mechanically. Now, mechanical auger is shown here, just a sample, and the typical dimensions of the holes that are created, which are called as a bore holes, BH bore holes, is 20 centimeter in diameter. 15 to 20 centimeter is the usual range of the diameter that you can expect from a bore hole made using an auger boring. It can be used up to 6 meters only for manual operation and 12 meters for mechanical operations, which means men at work would find it difficult to auger more than 6 meter depth because the soil gets stiffer and it'll be very taxing to screw this thing down into the soil. So it's limited to 6 meters when you're applying manual augering process, and it's limited to 12 meters when you go for the mechanical operation. They're applicable only for self-standing soil, which does not collapse in the absence of drilling mud. Now, drilling mud is some kind of a paste kind of thing. If you can imagine Colgate paste or any other paste, it's kind of a paste kind of thing, which when applied into the hole will enable this cavity formed to be stable. The usual thing that we use is a bentonite slurry. So that slurry mechanism is used to ensure that the cavity doesn't collapse. So it's useful, this method is useful for exploration of small depths like highways and railways, where the depth of exploration is quite low. Auger boring do have the advantage that it's rapid and economical. But the disadvantage, the predominant disadvantage, is that the soil gets disturbed and the strata changes that come across are hard to locate. So it's rapid and economical, but at the same time, the soil that you extract using these borehole mechanisms are disturbed. We don't know at what depth you have encountered, and the precise properties of the soil would be difficult to quantify. So it's a disadvantage. Now, the second method is a wash boring. In this, you first make a hole by inserting a casing, and you have a hollow drill rod with a chisel shaped chopping bit which you insert into the casing. Now there's an editing mistake here. It's not frill rod, it's drill rod. So there's a drill rod which is having a chisel shaped chopping bit, and you insert it into the casing. Now there's a schematic picture here. I'm not quite sure if you are able to make out what's written there, but anyways, the thing that you see at the center is a hollow drill rod, and it is housed inside the casing. So first you insert a casing there into the soil, and then you insert a drill rod into the cavity thus created. Now subsequently, water is pumped down through the drill rod using a wash pipe. So there's a mechanism through which you can provide water into it. So that's why it's called a wash boring method. And the hole is advanced downward by combined action of chisel chopping and water jetting, which means this mechanism allows water jetting through the bottom, which loosens the soil, and at the same time the chisel that is on the drill rod is operated up and down, and it loosens the soil further. So the soil that was at the borehole bottom, which got loosened using the water jetting and the chisel action, it's transported up towards the ground level, right? So imagine there's a water jet passing down to the borehole, it loosens the soil, and it is added by the combined action of chiseling, by up and down dropping of the chisel. So it gets further loosened, and this loosened soil is transported upwards by the slurry, the water, onto the ground level. So fundamentally you are transferring the mix of water and soil to the ground level. So they rise up the space between the drill rod and the casing to the surface. Now this is a photograph where wash boring mechanism is employed, and the hole is further advanced by dropping the chopping bit from a height. So the chopping bit is dropped from a height, and water jetting is employed, which loosens the soil, and soil is taken upwards. So instead of casing pipes, bentonite slurry may also be used to support the walls of the borehole at times. The advantage of wash boring is that it's light and inexpensive equipment, and the reaction from the drill bit gives an indication of the strata change, which means, just imagine you are dropping the drill bit up and down, and when it encounters a hard strata, the drill bit will show resistance, which means the layer on which the drill bit is resting is hard. So it indicates a hard strata there. Likewise, if it doesn't offer a resistance, it means that you are encountering a soft strata. So fundamentally, the drill bit's resistance gives an indication of the strata change. Its disadvantage is that it's slow in stiff soil and rock. And of course, the sample collected is disturbed because you are operating the chisel and the water jetting, and everything that you get is a mixed up kind of thing, a slurry kind of thing. So you don't have an option to make out what sample that you have collected, etc., etc. So these two methods, the auger boring and wash boring methods, are two different methods included in your syllabus. Anyways, you do have different methods other than what is mentioned in your syllabus. So if you're curious, you can just actually go through any standard textbooks or maybe YouTube videos on different techniques that's being followed, that's being practiced. Now the next test is quite important, standard penetration test. It's very important for your syllabus and also as a practicing engineer who is interested to design different foundations. Now standard penetration test, a schematic picture is shown here. This one is the most common test in practice for in situ penetration test. It's called in situ penetration because in situ meaning at the site. Penetration means you are penetrating something into the soil. So if you can see this picture, there is a ground surface here, there's a drill rod there, there's an anvil, and there's a hammer. So what you do is you pull this hammer up and allow it to fall freely onto the anvil. So the anvil is part of a drill rod. So what really happens is that the hammer kind of dynamically drive this drill road into the soil. Now, like I said, it's the most common in situ penetration test, and below the drill road you have what is called as a split spoon sampler. So the split spoon sampler is here, above which you do have the drill road, and you are driving the entire thing using a drop hammer. Now the idea is quite simple. The sampler is made to penetrate 15 centimeter by blows from a drop hammer of 63.5 kilograms falling from 75 centimeter at 30 blows per minute. Now these specifications are quite important. 15 centimeter penetration, 63.5 kilograms of weight, 75 centimeters of free fall, and 30 blows per minute. All these affect the data that you get from the field. Now, after an initial penetration of 15 centimeter, the number of blows N required for 30 centimeter penetration is noted. So I'll explain what it really means. First you create a borehole, let's say at 1 meter depth, using the auger boring. So you have a borehole here at 1 meter depth using auger boring, into which you place the split spoon sampler. I have a photograph of that in the subsequent slides. I think it's here. Yeah. So this is a split spoon sampler. In field photograph, it looks like this. It's called split spoon because you can actually split it. It looks like a tube, but you can split it into two longitudinally. So the split spoon sampler is kept at 1 meter depth in our story, and you drive the drill road 15 centimeters by drops of the hammer, specifications given here. So once you drive it 15 centimeter, you drive the next 15 centimeter, and you drive the next 15 centimeter. So what you do is at 1 meter, you drive the split spoon sampler to 45 centimeters, 15, 15, 15, and you neglect the first 15 centimeter and account the 30 centimeter that remains. So N value, the number of blows which is required for the 30 centimeter penetration, is noted down. The first 15 centimeter you neglect. The 30 centimeter penetration which follows, you are interested to get the number of blows required for that, which is called as an N value. SPT N value is what we call that. And this is a schematic picture of a split spoon sampler. If you are not able to make out from the fade figure that is given in the slide, you can just Google the figure and you will get a better picture, or you can refer to the standard textbooks. Anyways, this is an actual photograph of the split spoon sampler, and it's 450 millimeter or 45 centimeter long. The length is 45 centimeters. Outer diameter is 50 millimeters or 5 centimeters diameter, and the inside diameter is 38 millimeter, 3.8 centimeters. So just try to have a feel of the dimension of that split spoon sampler. And there's a shoe there, this portion, which is 7.5 centimeter long or 75 millimeters long. So the shoe enables the easy driving of the split spoon sampler. There are of course details marked in this picture. It does have a ball valve. It have the mechanism which enable the easy extraction of the sample. But what you need to know is it's 45 centimeter long, 50 millimeter outer dia and 38 millimeter inner dia, with a shoe at the bottom which is 7.5 centimeter long. So the procedure is like this. Again, you have the photograph which I've taken from the internet. This one is the hammer. There's an anvil beneath that, below which you have the drill road, and there's a split spoon sampler which is not given in the photograph because it's inside the hole. So there's an operator here operating this mechanism. What he fundamentally does is that he allows the drop hammer to move up and allows it to drop freely. So you drill the borehole to the required depth, clean the borehole thoroughly, and the split spoon sampler is attached to the rods and lowered into the bottom of the hole. So you have the borehole created in the figure. You clean the borehole thoroughly, not using water of course. You take out any sample that is left over there, and the split spoon sampler is attached to the rod here and lowered to the bottom of the borehole. And the drive assembly is connected to the rod, and the hammer is allowed to fall on the sampler. The hammer is allowed to fall, of course, on the anvil, which is connected to the rod, which is connected to the split spoon sampler. The drive assembly is thus connected, and the number of blows required to penetrate 30 cm after a seating of 15 cm is taken as the SPT end number. Like I said in the previous section, you ignore the 15 cm initially, you take the number of blows that's required to penetrate the 30 cm further out of the total 45 cm you penetrate. And then the sampler is lifted to the ground level, and the soil which is inside the sampler is carefully taken and tested in the laboratory. So in the previous photographs we had seen that the sampler is split kind of thing, which means it's cylindrical in shape, outer diameter 50, inner diameter 38, and it can be split into two portions. So the soil which has gone into the sampler, which is undisturbed, and it's carefully taken and tested in the laboratory. The usual test that we do is a triaxial test, based on which you will get C, cohesion, and phi, internal friction. So this photograph was taken just 1 week back. It's a site at Adimali. So Adimali, at that site, we had to take a few SPT numbers. SPT tests had to be carried out. So I thought I'll take a photograph for you to understand it, the real scale of the picture. Now, this is a hammer here. I'm sorry, there's no proper lighting there. So anyways, if you can see, there's a hammer here, and there's a wire rope here. You can actually pull the wire rope up, and the hammer goes up, and it gets dropped by the laborers. So these are extension rods which are used to extend this. Once you drill, let's say 2 meter, you need to extend that downward. So at this particular site, the drill rods had to be extended to 15 and 20 meters into the soil. So just thought of sharing this picture in case you're interested to know about the real procedure. Now there are different corrections here. Corrections for N value is because it's influenced by the borehole diameter, the length of the rod, the effective overburden pressure, etc. So though there are different corrections like borehole diameter correction, length of the rod corrections, the one thing that's included in your syllabus is limited to the corrections of overburden and dilatancy. So the original N value is corrected to get the corrected N value marked as N corrected, NC. So number one is overburden correction. It's marked as NC is equal to N into 350 by sigma dash plus 70, where sigma dash is the effective overburden stress, which is not exceeding 280 kilopascal. So if it exceeds 280 kilopascal, you take it at 280 kilopascals as well. Now that's an overburden correction. And second one is a dilatancy correction. Dilatancy correction means when you have the test carried out for silty sand below the water table, you apply the dilatancy correction. It's NC is equal to 15 plus N minus 15 into half. So this is applied when you have the silty sand below the water table. And there's a clause here. If N is less than 15, you take NZ as N itself. So for every value of N less than 15, N corrected have to be that value itself. You don't have to apply the correction. Now, next one is the SPT correlation, which means based on the corrected N value, you can get different engineering parameters which will help you to design different foundations and other structures. N value, of course, is an indication of how the relative density changes and the angle of internal friction of sand and the uses of clay. So hence it can be indirectly used to calculate the bearing capacity of the soil and the pile capacity. These are just examples anyways. roughly you can take QU in kilopascals as 12.5 N corrected. And I've added a table here which correlates N value to QU value in kilopascals. For N value 2, you can take QU as 25. For N value 30, you can take QU as 400, etc. But there's a cautionary note that I'd like to add. These are just indicative. There are different correlations available in different textbooks, and different charts and tables are available. It's your choice, your engineering judgment that decides the precise choice of these values. There's no blind choice. There's no one size fits for all kind of a formula here. You need to have a feel at the site. You need to have proper engineering judgment to arrive at these conclusions and to choose which one to go for. So there's another correlation here. N correlated to phi, angle of internal friction. For N value 4, it's roughly 32 degrees. For N value 50, it's roughly 45 degrees, etc. So these are different SPT correlations that you can use for designing of different structures.